Hello, SWIC Earth Science students. Welcome to the next recorded lecture. This week, in week 8, we will be looking at earthquakes and Earth's interior, which is chapter 5. I also include tsunamis in this section. Your book covers tsunamis, but not very much in detail. I talk more about tsunamis than your book will. Again, make sure to read the text. I'm a seismologist. Earthquakes are my jam, so I will really be getting quite a bit into this. I will cover the Earth's interior fairly quickly because I covered that rather thoroughly in the plate tectonics week. So you will see the same slides from the plate tectonics week, and I will go through them fairly quickly. So remember, the internal structure of the Earth is layered. We have physical or mechanical layers, and then we have chemical layers. The boundaries between these are not going to be the same. Let me actually pull up my pen. All right, so the only boundary that will be the same between them is this boundary between the mesosphere and the outer core, or the mantle and the core. That is the only boundary that's going to be the same in both layers. So we have chemically crust. This is our most variable layer. This is where we stay. It's the very thin outer layer of the planet. We have a rocky mantle. It is separated from the crust by the moho. The mantle has mechanical layers, and it's the majority of the planet. It's the largest volume of the planet, about 82% of the planet. And then we have the core, which again we see has mechanical layers. Our physical layers, I apologize, the text is smaller on this version of the slide than it is in the plate tectonics version. Mechanical layers, we have lithosphere, which is variable. This is the rocky outer shell. It has the crust, which is variable in thickness between ocean and continent, and the uppermost part of the mantle. We call that the mantle lithosphere. Sometimes it's called the lithospheric lid to the mantle. Below that is the asthenosphere. The asthenosphere is the weak part of a mantle that is very easy to convect. It can flow over geologic time. The boundary between the lithosphere and asthenosphere is the LAB. Then we have the mesosphere. The mesosphere is where the mantle regains its strength. It's the lower part of the mantle. Here, convection can still occur. It's not as strong as what we see in the asthenosphere. And then we have our two core layers. We have a liquid outer core. This is why we have a magnetic field. And then we have a solid inner core, which also helps with our magnetic field. Both the cores are nickel and iron. So the way that we have flow within the mantle is convection. Remember, convection is where we're going to transfer heat by moving actual particles. So in the mantle, we have actual rock moving up towards the mid-ocean ridges. We will create new crust at the lithosphere. It will then move along and it will eventually come down in a subduction zone and then come back into the mantle. So we will see these cycles of movement of heat due to moving actual material throughout the mantle. And that's what we mean by convection. We will come back to convection again in when we talk about weather. How do we know about the layers of the planet? It's seismology. I talked about this during plate tectonics, so we are going to learn today that there are different types of seismic waves. There are two types of what we call body waves. Body waves move through the interior of the Earth, the body of the Earth. We call them P and S waves. S waves can't move through liquid, which means that when an S wave, which are these black lines, encounter the liquid outer core, they stop. So they see that they stop here. They're not actually going through. And that means there will end up being an area of the planet, actually it's this entire area down here, where we will not see S waves because they are being deflected. They're being stopped. I could have just done that on this one. So these S waves are being stopped by this outer core, and so we will not see S waves on the far side of the planet, or rather direct S waves. That means that there has to be something liquid inside the planet. the way we find these different boundaries within the planet for all the different layers is also how other seismic waves react. Because every time seismic waves hit a boundary, they will change their velocity, and that velocity will tell us about the properties they're going through. So oceans and continents are different. Remember, this is a little bit out of place. The main thing is the composition. So the oceanic crust is made up of salt. That's that mafic rock. It is, I've lost my thing. There it is. It is higher density. So this is going to be horrible. Mafic. I am bad at writing with my mouse. So the oceanic crust is mafic. It is more dense. It will be a little bit lower elevation-wise, which is why the water sits on top of it. Continental crust is felsic. It is lighter in color and in density, so it will be thicker to balance out this more dense oceanic crust, and it will not want to subduct. We don't get rid of oceanic continent. So, that oceanic continent is nothing. We do not get rid of continental crust. Oceanic crust, however, being more dense, it likes to subduct. So that is where we see that difference in the age, that the continental crust will never really be destroyed, so it can be much, much older. We have pieces of continental crust that are 4 billion years old, whereas the ocean is constantly being recycled. It's constantly being subducted. So our oldest ocean is only about 200 million years. So this is just 200, and this can be 4 billion. So there's a big difference there. And then again, this all comes back to the composition, that we have that felsic versus mafic. So now we're going to talk about earthquakes for the rest of the day. Yay! I love earthquakes. That was a weird thing to say. It is true though. I like earthquakes. I like to study them. It's an unfortunate thing that when you study one of these things that's related to a natural hazard, you are actually excited when they happen. You feel bad for the people they're happening to, but we learn a lot from them, and that helps us in the next time we have a massive event. So first we're going to see a recorded video from a magnitude 7 earthquake that occurred in Anchorage, Alaska in 2018. So this is also posted on the YouTube channel.
Chaos in the courtroom. Cameras were rolling when the quake struck at 8:30 a.m. Alaska time. Ceiling tiles fell, the lights dimmed out, and look, there's a woman hiding under her desk. And outside the courtroom, watch as these security officers take shelter under tables. The quake struck as students were beginning the school day. They had to hide under desks.
Hold on to the table. Hold on.
There were tense moments in the air as a pilot is told to turn around.
Let's go around. Going around.
TV newsrooms were in total disarray as power knocked them off the air. A reporter at the CBS station had to rely on Facebook Live to broadcast the damage in their newsroom.
You can see this room. Everything, ceiling tiles have fallen, monitors, TVs, what have you, scary situation.
Many roads and highways looked as if they'd been gouged out. And look at these home security videos. You can hear children screaming inside as this home shakes and the family flees for the basement. A young man yelled out in distress as his room began to rumble around him.
Oh, crap!
And this frantic mom grabbed her son and embraced him as their dining room lamp swayed back and forth. Scary scenes that these folks will likely remember for a lifetime.
Overdue. It's overdue.
So this is another video of the aftermath of that same earthquake. I do want to point out, in that video, you saw people doing different things. In an earthquake, what you want to do is you want to get under something that's nice and solid and isn't going to move, and hold on to it so that if debris falls on top of you, that it's not crushing you. So getting under a solid table, going to a door frame is one of the things that people like to recommend. Getting to an interior bathroom in the door frame where you don't have glass, you don't have a lot of problems like that. You don't necessarily want to go to a basement, because if your house does collapse, now you have the entire rubble on top of you. So basement may not be the best place to go, but you do want to get away from glass windows in case they break. You want to make sure that anything that could fall on you, that there's something to protect you from that. So what to do in an earthquake. Again, this is going to be someone driving around after the earthquake and looking at the roads and things. This is that airport again. They lost power. This is in a warehouse.
Yeah.
So these are the roads afterwards. That car obviously was on the road when it collapsed. That car was obviously on the road when it collapsed.
Got a house on fire there. Ain't nothing left of that thing. Pray that nobody died.
I want you guys around that post.
Oh.
So fires, we will see, can also...
Hey, NBC News viewers, thanks for checking.
Don't want to watch that. Fires can be something that happens after earthquakes. We will see that. When you have an earthquake, you are shaking and rupturing the ground. So if you have gas lines, you can break those gas lines. And then you now have gas that's highly flammable that can then be sparked by if you break, say, electrical lines. So that is... something that happens after a lot of earthquakes. So earthquakes we're going to see are something that we end up having other things happening afterwards, and I'll talk about that all today. So this next video is going to be, this is from 2012 maybe, and it's showing the earthquakes for the past 15 years. I think it pulls up what date it is, but we are going to see, as we can see from the screenshot, you can't see my pointer very well, oh, it's a finger now, okay. You will see the outlines of the plate boundaries very well. There are some of these big ones that I will point out when I will try to point out the big ones as they come up. Most of the big ones we see are in subduction zones. They outline the subduction zones because that's where we see our largest earthquakes, and I will talk about that today. The color will indicate the depth. So the hot colors, the red colors, are shallower earthquakes. We only see shallow earthquakes along our ridges. We do not see deep earthquakes along the ridges. The cooler colors are going to be our deeper earthquakes. So those are the blues and the purples. Those will only be seen along the subduction zones. If you remember from the plate tectonics lab, it asked you, why do we see earthquakes down to 600 meters? It's because they're in a subduction zone. And the size of the circle will indicate the size of the earthquake. So this giant orange one is Tohoku 2011. This giant orange one is Sumatra 2004. These were massive earthquakes. They're two of the 5 largest earthquakes, actually. So I will try to point these out as they happen. There is music in the background. It's rather dramatic music. So here we go. Okay, it's to 2015. So immediately, we have earthquakes constantly happening. They're happening all over the world. We see I pointed out with my finger, the date is down here. So there was a big one up at the collision zone between India and Eurasia. So we're in 2002 now. So we are seeing some of these bigger ones along the subduction zones. Only subduction zones, remember. We're in 2003. So there was a fairly big one in Japan there. Sumatra happens at the end of 2004, so it's going to be coming up pretty soon. But now we can see these ocean ridges are starting to be outlined. The subduction zones are very nicely outlined. And there's Sumatra. Sumatra is the 3rd largest, I believe it's still the 3rd largest, recorded earthquake. So we see some of those big ones happening in the different subduction zones. Often we tend to see aftershocks, so we'll see one big one, then we see a couple of other fairly large ones directly after it. We will talk about that today. We're also seeing quite a few in Hawaii. Hawaii does have a lot of volcano, or it has a lot of earthquakes related to the volcano. They tend to be fairly small. There was another big one in Sumatra. So we see the more earthquakes are happening in the subduction zones than happen on the mid-ocean ridges, but we do see the mid-ocean ridges being outlined as well. They're not quite as constant as in the subduction zones. You know, the subduction zones have them happening all the time. Oh, I want to point out Haiti. So Haiti happens in 2010. So Haiti's going to be over here. I might have just missed it. I missed it. Haiti was not that big. Okay, there was Tohoku, which was the 4th largest, I believe, earthquake. So the one that happened in Haiti was so small that I barely could pull it out as being a major earthquake, but it caused major damage because of where it happened. So we're going to see that the amount of damage is really going to depend on where they happen, as well as the size. And this is almost finished now. We're in 2014. So we could do a more updated one that would basically be showing the same patterns. You know, we have these patterns happening all the time. Earthquakes happen all the time. We see the big ones in the same areas all the time. Now this is all of the earthquakes. So we see those plate boundaries outlined very well. Next, it will show us all the large earthquakes. So these are all the ones greater than a 6.5. We see most of these are concentrated in those subduction zones. So that's Haiti, the one that caused all the problems. And then these are greater than 8. So that one in Haiti was actually a fairly small earthquake, relatively. All of the ones greater than 8 happen in subduction zones. We only get those massive earthquakes in subduction zones. I like that video a lot. All right, why did you not go through? All right, earthquakes. Earthquakes are what is called a hazard. They are a natural hazard. So they can cause natural disasters. A disaster is a response to a hazard. The hazard is the actual thing. So these are called earthquake hazard maps. So this is the likelihood of a certain amount of shaking happening within a certain time period. So the one on this side is a 50-year map. This one is from 2014. This is a 1-year map, and it's for 2018. So the map on this side is saying that, you know, this 50-year one is saying that these areas that are hotter colors, the pinks, have a very high probability of a certain level of shaking occurring sometime within the next 50 years from 2014, because it was published in 2014. So we see very high hazard all the way along the west coast because we have active plate boundaries along the west coast. We see a high hazard in Hawaii. We see a high hazard in Alaska. And these other areas on the east coast where we see higher hazard are places where there have been earthquakes in the past. So there's an area of weakness in the crust there. So the New Madrid seismic zone, for example, or Charleston, South Carolina. It doesn't say when it's going to happen. It's just saying it's a high probability of happening in the next 50 years. Whereas this one over here is a single year map. So these are the areas that are likely to experience shaking within each year. It happens every year. So now we see a very different picture that we don't have it all along the west coast, but it is concentrated here in California. We now see that the hot spot on here, the highest amount of activity, is in Oklahoma. That is also on this other one, but it's not nearly as intense. This is because this part of Oklahoma experiences shaking due to fracking. So it is due to human interaction. If you looked at a map from 20 or 30 years ago, you would not see any activity in this region. This is purely due to human intervention. And and it happens very small amounts of shaking, but it happens constantly. It's very frequent. So it is going to happen every year until we stop our activities that are causing it. But it's not a high hazard. It's not really dangerous. So that's why it's not nearly as intense on the 50-year map. So these are published every year, and they basically tell us what areas have this potential for a problem. We make hazard maps for every type of natural hazard. Earthquakes may be the most well known. I'm not sure. But that's what these mean. These are all probability maps. It's not a prediction, a true prediction that there is going to be an earthquake in this location. It is a probability that there will be one in a certain time frame. This is a list of notable earthquakes in the U.S. It has the year they happened, where it happened, the amount of damage in dollars, and the number of deaths. I want to point out that this one here, New Madrid, I can't draw a straight line, 1811, 1812, that is the largest, what is known as intraplate earthquake, meaning it happened in the middle of a plate in history. We did not have instruments in 1811 and 1812, so all of our knowledge about it is from reports. There were reports of church bells ringing in Boston due to this earthquake. So the shaking propagated very far. So this 1886 Charleston, South Carolina one is why Charleston. So these two are historic earthquakes, and they're why we have on this map, we have these areas where we have the potential for seismicity because we've had seismicity there in the past. Many other ones are going to be in California. This 1964 one, we will see a video about this. Most of the deaths that occurred in this one, this is the second largest earthquake ever recorded. Many of the deaths are associated with a tsunami. And that is a very important earthquake for actually our understanding of the Earth. San Fernando in 1971 had quite a high death count because of it was unexpected. Loma Prieta in 1989 was the same idea, that we did not realize there was a fault there, and so people weren't necessarily prepared, so higher death count. Northridge. So we're going to see that the death count tends to go down except in these cases where we have a we get caught off guard. So the death count goes down very drastically. We see, well, these are all similar death counts. They're happening 10 years apart or 20 years apart between each one, but we improve things. Things get better. If we pull up the Wikipedia page for earthquakes in California, you will see that the more recent ones have lower death counts because we have prepared for them. We have learned from these past ones. I want to point out that the textbook that I took much of this information from was very U.S. centric, so some of these things will be like this is specific U.S. Earthquakes. I will talk about next the largest recorded earthquakes. So Chile, 1960. Subduction zone. Prince William Sound, Alaska, 1964. Subduction zone. Sumatra, 2004. Subduction zone. Tohoku, 2011. Subduction zone. Kamchatka, also subduction zone, 1952. So these three all happen in the early ages of our technology. So 1952, 1960, and 1964, we didn't have the best instruments at that point. They were still the old-fashioned drawing the wiggles on a piece of paper with a stylus. Whereas 2004 and 2011, we had digital instruments. So you will see variations in the magnitude sizes. Also, it's a little bit difficult to calculate an accurate magnitude for this large of an earthquake. So sometimes you see these presented as different numbers. I'm trying to remember what number they use in the video I will show you. I will show you a video on this one, and they name it after the magnitude. And I'm trying to remember, it might be 9.4 that they name it. But you will see different numbers. This is the order they typically will put them in. So we have had 5 magnitude 9s in the past 70 years. Luckily, we don't tend to have magnitude 9s all that often because these are massive earthquakes, and we will see that. The largest earthquakes, I got this from Wikipedia. These are the largest earthquakes, including historic earthquakes. So we will see estimate on a bunch of these. If we look at that, these are all going to be before recorded, instruments. So these are when we don't have scientific instruments, so we can't get a very good. We're doing this based on historical records. So there have been more magnitude 9s in recorded history, but in recorded human history. But scientifically recorded, we only have those 5 magnitude 9s. This Kamchatka one is probably smaller than this one from 1730, so that's why it got pushed down a little bit. So all of these are happening in subduction zones. These are, the largest one on here is an 8.7. These are all happening in subduction zones. We only get these massive earthquakes in subduction zones. And we see that they happen in similar places. Let me point out, Cascadia, do you know where Cascadia is? That's Pacific Northwest. This is a big earthquake. There will be another one in that area at some point. So that is a problem. So if we look at the deadliest earthquakes, now if we look at our magnitude, they are not that big. So the only one that is above a 9 is going to be this guy, which is Sumatra. And most of that death toll comes from the tsunami that came after the earthquake. So when we look at these fatalities, most of these are actually something else. It's not directly from the earthquake. I have not looked up the stats on the Turkey earthquakes that just occurred, so those are not on any of these charts. This largest or deadliest earthquake weather that happened in China, the reason so many people died was the building practices. So this was obviously a historic earthquake from 1556. The area where it occurred, the building practice was to build into the hillsides. The hillsides were a type of material called loess. It's a wind-blown sediment. So it's very, very fine grained. And when you start to shake it, it will undergo a process called liquefaction, that it basically, when you shake it, it turns into a fluid. And so when this earthquake occurred, the hillsides basically became fluid and buried entire towns. So it just decimated the area. So the earthquake itself is an 8, which is a large earthquake. It's a great earthquake, but it's not a 9. We're going to see that each step on the scale is logarithmic. A 9 is 10 times bigger than an 8. So again, it was the building practices why we had so much impact on fatalities. Many of these are happening in areas where they're just not prepared, or they have not as stringent building practices. If we look at these, most of these are also older. So 1976 is fairly recent. 1920 is at least this or last century. 2004 is fairly recent. 2010 I think it is the most recent. So this one in Haiti, again, not that big of an earthquake. A 7 is not that big of an earthquake. And I think it's actually been downgraded from that. It's the building practices that the buildings just collapsed and killed many, many people. 1948, again, that was building practices. 1923, this is in Japan, the Kanto earthquake. That earthquake was a wake-up call for Japan, and Japan, there's another one that happens as well, Kobe. But Japan, after they have these big earthquakes, they really ramp up their technology and their studies, so they get better with each one. If Tohoku had happened anywhere other than Japan, its death toll would have been significantly higher. And notice Tohoku is not on here. Prince William Sound also isn't on here because it was in a sparsely populated area. Costliest earthquakes. Now Tohoku is on here. Tohoku is number 1. If we look at the costliest, again, our magnitudes, Tohoku is a big one. The next largest one is going to be this 8.8 in Chile, which happened in 2010. Most of the other ones are not that big. But if we look at the dates, these are all fairly recent. So 1995 that would be Kobe, actually, I think. So that's in Japan. Um, let's see, 1999. I'm looking for ones that are not in this century. 1980, 1994, 1976, 1999. Honestly, the 1906 San Francisco earthquake is the oldest one on here. These are all in the last 2 centuries, this century and last century. So most of them are in the past like 40 years or so. So the 1906 and 1923, which are the two lowest on here, are the oldest ones on here. Most of these are happening, honestly, in my lifetime. But these are all fairly recent earthquakes. And they're not necessarily huge. So the size is not going to necessarily dictate how expensive it is in property damage, nor will it dictate how expensive it is in lives. So if we look at largest versus deadliest versus costliest, we do not see the same event on all three of these. No one event is found on all three of these. We will see Tohoku is costliest, and it is on the largest, not largest. We will see, let's see, I think Haiti is on both. Is Haiti on? No, that's Chile. No, Haiti's not on both. It's just deadly. We will see the Sumatra is on largest and deadliest. Where are you at? It's over here. Let's see here. 2010 Chile are large and costly as well. So where's 2010 Chile? So 2010 Chile is on here, and then it's costly, so 2010 Chile. And then we will see that Kanto is deadly and costly. So here's the Great Kanto and the Great Kanto. But we don't see the same event on all three. So size is not going to dictate that just because it's big doesn't mean it's going to be very costly or cause a lot of death. Just because it caused a lot of death does not mean it's going to be cause a lot of property damage. It's going to depend on the building practices a lot. So most of these costly ones are happening in more developed areas, and that is because the developed areas are prepared for the earthquakes, but it costs a lot in order to have your buildings be more earthquake resistant. So when they need to be repaired, it's also costly. Whereas if you decimate a country that's not as developed, or a city that's not as developed, it doesn't cost as much to rebuild it. If you decimate Tokyo, it's going to cost a lot to rebuild it because it cost a lot to build it in the first place. Deadly is, again, not going to be necessarily costly because if a lot of people have died, you probably don't have those really good building practices, and that's why all the buildings collapsed. Those buildings are cheap to rebuild, but they end up killing a lot of people. And size does not necessarily dictate either of those. Depending on where it happens, there may not be significant damage. If it's like Prince William Sound is happening in a very isolated area, it's not going to it causes damage in the area it's in. It's just there aren't a lot of buildings there, not a lot of people there. So we talk about earthquakes because every continent experiences seismicity, including Antarctica. That's what I wrote my dissertation on, actually. Every continent has seismicity. Every plate has seismicity. Our plate boundaries will be outlined by seismicity. Earthquakes happen in concentrated areas, but they happen all over the world in concentrated areas, though. So almost every country will experience some sort of seismicity. There are some countries in Africa that probably have not had seismicity because they're in the middle of a plate, or they may be far enough away from those boundaries. But definitely every continent, but almost every country experiences some sort of seismicity. Earthquake terminology. So I use the term event often because being a seismologist, I look at things that make seismic waves, which aren't always an earthquake. So an event is anything that produces seismic waves, which are the energy that propagate through the earth. So often they are earthquakes, but they can be other things as well. A fault is the area of crust that will break or fail that then produces the earthquake and the seismic waves. A fault block is the area on either side of that fault. So this is the fault. These are the fault blocks. The hanging wall is the part that's above the fault. So it's on top of the fault. The footwall is the part below the fault. The terminology comes from mining. So you would stand on the footwall, hence footwall, and you would hang your lantern on the hanging wall. So hanging wall is going to be above, footwall will be below. Depending on how they move is what we're going to call the fault. Additional terminology. Faulting is the process of the fault breaking or moving. Stress is the force per unit area that acts on a surface. So this tells us the conditions of a fault. So once a threshold or minimum stress is reached, the fault will break. So if you take a popsicle stick and you start bending it, it will bend a little bit, but eventually you will put enough pressure on either end of it that it will snap. That's the same thing that happens in the earth. Strain is the response of stress. So it is changes in the shape, size, or location of materials in response to stress. So again, stress will be pushing on the ends of the popsicle stick. Strain is the middle bending before it finally breaks. There are 3 types of stress that cause 3 different types of earthquakes. We also have 3 types of plate boundaries, I might add. So tensional is where you're pulling things apart. So this is tension, you're pulling. Compressional is where we're pushing things together. So you're pushing them together. So, oh, I can draw. So this is tensional, we're pulling apart. This is compressional. I'm sorry, it's angled, we're pushing together. And then shearing is when we are sliding things past each other. So we have 3 types of stress, 3 types of fault, and 3 types of plate boundaries, it turns out. So tensional, we are pulling things apart. So we are going to pull them apart. When we do that, the hanging wall will drop down with gravity. So this is called a normal fault. Compressional is where we are pushing things together. So when we push things together, the hanging wall tends to move up against gravity. We call this a reverse fault. Oh, I can underline these. And then shearing stress, we will just slide our things past each other. I did that wrong. It's going that way. So we will slide things past each other. So we don't actually have a hanging wall and a footwall in this case. We call this a strike slip fault. So strike is the direction of the fault as a line. For a strike slip fault, we are moving the blocks along the direction of the fault. These other 2 are called dip slip because they are slipping along the angle of the fault, which is called the dip. So we have 3 types of stress. So we have our tensional stress. We have 3 types of faults. Tensional causes normal faults. And we have 3 types of plate boundaries where we tend to have this happening. Divergent boundaries are pulling apart in tension. We tend to have normal faults at our divergent boundaries. We have compressional stress, which is our reverse faults. This is where you have 2 things coming together. They're pushing in together. And these happen often at convergent boundaries where we have 2 plates coming together. And then our 3rd type of stress is called shearing. These make what are called strike slip because again we're slipping along the strike of our fault. We're not going up or down. And these tend to happen at transform boundaries where you have 2 plates sliding past each other. You will see this slide again many times. Know this slide, I will add. We can have hidden dangers in faults. So if we don't know a fault is there, if we don't actually see the fault exposed at the surface, like the San Andreas, you can see the fault. You actually see it along the surface. You can go put your finger on it. We sometimes have what we call blind faults, that the fault is there, but it's beneath the surface. We can't actually see it. We now know, thanks to some of these deadly earthquakes that happened in the past on this type of a fault, we now know that when you have what is called a blind fault at depth, so it's blind because it hasn't actually intersected the surface, it stops, they tend to make this uplifted area on top of them. So now we know that. So we can see these things and recognize that there's probably a fault at depth or potentially a fault at depth. Until we had some of these events like Northridge 1994, this relationship wasn't recognized. Now it's recognized, so we're caught off guard less frequently. It's still possible to be caught off guard. And it's called a blind fault because, again, we don't see the actual fault exposed at the surface. So we don't realize that that is a potential hazard area. There's a question, are any faults safe? Oh, this is a perfect example to use right now. Active is whether or not it's moved in 10,000 years. 10,000 years is a long time. That's longer than recorded human history. Potentially active is if it's moved in the past million years. Okay, that is, back into different geologic periods. Inactive if it hasn't moved in the past 2 million years. Okay, that's a long time. How can we tell if it has moved? Paleoseismology is the tool. So paleoseismology is looking at the Earth and seeing how it's recorded past seismic events. So we can look to see ancient faults. We can see them recorded in the Earth. We can see evidence of past earthquakes. We can also look for more recent ones, human writings. So for example, Japan has amazing records. They record almost every earthquake in their journals. So we can actually look at past events that way, if it's in human recorded history. The problem is that even if a fault can be proved to be, quote, inactive, so it hasn't moved in the past 2 million years, it's still a fracture in the crust. It's still weakness. So there's the potential for movement on that fault because the Earth is always going to follow the path of least resistance. It's much easier to re-break something that's already been broken once than to break new ground. A perfect example of this is the North Anatolian Fault in Turkey, where there have been several earthquakes in 2023, recently in 2023. So for the longest time, this fault hadn't had any movement. There's a long history of civilization in this area that has written records, and it was thought that this was inactive until it started going off in the 20th century, and it caught people off guard because they knew the fault was there, but they thought it was an extinct fault. It's not extinct. And during these early events, this is before plate tectonics, so they didn't realize why there was a big long fault here. So even if you think it's extinct, it's not necessarily dead. So no faults are truly safe. They can always be reactivated because they are that weakness, but often it's just that there's a long time between events. So what is the actual earthquake? The earthquake is the actual breaking of the fault, movement of our two blocks past each other. The movement will then create seismic waves, which are the energy waves that will propagate out radially, meaning in all directions, from where the earthquake occurred. So we refer to the seismic waves themselves as the earthquake as well. So we'll talk about the earthquake as being the seismic recordings. The fault will break at what's called the focus. It's also called the hypocenter. So these are the same location. This is the actual spot where the crust cracks. If we project that spot up onto the surface, that is called the epicenter. Typically on the news, they report the epicenter. The way I keep them separate is that epi means surface. It's like your epidermis, which is your skin, your surface layer. Whereas hypo is center, so that's going to be where it's actually starting. Focus is the other term for that. And again, the seismic waves will move out radially in all directions. They may move faster or slower in certain directions, but they go in all directions, including down into the earth. So the earthquake cycle is the bending of the Earth's crust, which will then cause breaking, which then generates the earthquakes. So elastic strain is strain that can be recovered from. So if you take that popsicle stick and you bend it just a little bit and you release it, it will go back to being straight. The Earth can do that too. So you can start to bend the Earth, and if you release the strain, it will go back. So this is what we call elastic strain. If we keep bending the Earth, like what we're seeing here, that we have this side is going to move in this direction and that side will move in that direction. If we released that strain, that stress, it would snap back to this location. It would recover. But if we overcome the threshold stress, eventually we will have sliding, that we will actually have fast movement on either side of this block. Now, do you see this curvature here? After we have that movement, the actual sliding on the block is the earthquake. But after we have this movement, we have released the stress. And so now this curved part of the surface will snap back to being straight, and that also contributes to the earthquake. So we call that elastic rebound, that we will snap back to no longer being deformed after the earthquake, and that's what produces our seismic waves that then propagate out and can cause damage. So the earthquake is not just a single earthquake. The earthquake is going to be potentially a main shock, which is the big earthquake, and then we will have foreshocks and aftershocks. All of these will be determined after the fact. So this is an example from Tohoku. So we had earthquakes. This bottom one is showing us the earthquakes. The size is indicated by the circle, as well as, or the size of the circle, as well as the vertical scale. And then the bottom, or the horizontal scale, is the date. So we can see that a lot of earthquakes occurred before this main massive earthquake. But we didn't know that those were foreshocks until we had the big one. And now that we plot them, we can go, oh, those are foreshocks. That is happening as a foreshock. Aftershocks are much easier because they're coming after the main event, so we can say that all these things are happening after our main event. So here we have a map showing where they're actually happening off the coast of Japan here. This is all happening. Here's our trench. So this is a subduction zone. The reason we get aftershocks is that we are releasing stress in one area, which will actually push the stress to different areas. So you can then cause those areas to hit their threshold. Foreshocks are releasing stress too, so you may then be concentrating stress in the area where you would then have your massive event. But foreshocks are determined again after the fact. Aftershocks can be determined almost immediately because we know that we've had this big event. Sometimes the quote big event isn't actually the biggest event. So, for example, you may have something that looks like a main event and then you have a bigger one happening immediately after. So then you realize, nope, that wasn't the main event. That was actually a foreshock as well. So normally these are determined after the sequence has ended. So seismic waves. So this is the energy that propagates through the earth. There are two main types, and then there are a bunch of subtypes. Our main types are called body waves, meaning they move through the body of the earth, and surface waves, meaning they move along the surface of the earth. So body waves move through the earth. There are P waves, which stands for primary. Conveniently, these are compressional waves. So that's another way of remembering it. S waves stand for secondary because they come in after the primary waves, but they move by shear. So most S waves are called shear waves. Then we have surface waves, which move along the surface of the earth. They will be the product of body waves interacting with different surfaces. So these are called love waves and Rayleigh waves. The body waves cause the most damage. These are the things that really cause an impact. They come in last. So I will show a video as well, but basically these are different ways of demonstrating how these things move. A P wave being a compressional wave, which actually sound is also a compressional wave. It's moving through the air at 333 meters per second. So we are actually going to have the individual particles will move back and forth and compress on each other. A shear wave moves by the particles moving up and down like a snake. And then our surface waves tend to have a component of each of these. So that's where we have things like ground roll, that it's a rolling motion. So we have this type of a motion. So body waves will pass through the Earth's interior. The primary waves are P waves. They arrive first. They are the fastest. So I will show this in a second. They can move through solids, liquids, and gases. They can move through anything. My voice, again, is a compressional wave. It's moving through the gas of the atmosphere. Or rather of the atmosphere. the air. So this is going to move if we look at this individual block, it is deforming by being squeezed. And so we're moving the energy by squeezing these individual blocks. You can think about this as a slinky. If you pull a slinky out and you push it, you will not be moving the individual slinky, but you'll move the energy by bringing those springs closer together and further apart. So again, this is a compressional wave. It can move through any material. It will be slowest in liquids, and it'll be fastest in solids, and then in between in gases. It's dependent. I'm sorry, I think I said that wrong. No, it'll be slowest in gases, fastest in liquids or solids, and then intermediate in liquids. The more dense a material is, the faster it will move, because this is a resistance to compression. So there's not a lot of resistance to compression in gases. They can move around much more freely. There's not as much resistance to compression in liquids. There's a lot of resistance to compression in solids. So again, the important thing is that they can move through any material, and how fast they move through it tells us what the material is. The second type of body wave is an S wave, and I will add there are many different subtypes of these two. I'm not going to go into that. So S waves are secondary waves, but we typically call them shear waves because they move by shearing. So they will be slower than P waves, predictably slower than P waves too. So this is if you take a jump rope and you snap it, the rope itself is not moving, but you will have that loop basically moving along. So it will move like a snake. They can only move through solids because they are moving due to the resistance to change in shape. Liquids and gases do not resist the change in shape. Therefore, S waves cannot move through them. So this is how we're moving. If we look at our box, it is changing shape. It's the same volume, it's changing shape. And so liquids and gases do not resist a change in shape. Therefore, S waves cannot travel through them. They will stop. Our body waves our surface waves, I said that wrong, surface waves, they travel along Earth's exterior. So there are several types. The ones we talk mostly about are Rayleigh waves and Love waves. Rayleigh waves are caused by P waves interacting with the land surface. This causes a ripple, so we can see that there is that compressional, we're still squeezing it a bit, but we also will have this rolling motion. So these are the things that cause the most damage. They are only on the surface though. So one, you do not get these type of waves if you have a very deep earthquake because it's not interacting with the surface very much, and they do not impact very far down. These, however, can travel a great distance around the Earth. Here are love waves. Love waves are S waves interacting. So this is the ground is like wiggling like a snake. These, our surface waves in general are going to be the most destructive. These two will come in later and they will be the most destructive. And sometimes they come in at the same time. So these are what are going to cause the most damage. So here are again our three types of waves. The only one that goes through liquids is going to be a P wave. Rayleigh waves can somewhat go through liquids as well. These ones, actually love waves can too because they have a component P with them. S waves cannot go through liquids, so we're going to have these different waves will cause different impacts when they reach, or as they move through an area. For a large earthquake, these things will go for a very long time. So this is a record of looking at the bottom is showing the distance in angle. So 0 is where the earthquake started. 180 degrees is the opposite side of the earth from the earthquake. This is showing a record of the Rayleigh waves as they move across the earth. So R1 is the Rayleigh wave that moves from the earthquake around to the far side of the earth. R2 is the earthquake or the Rayleigh wave that moves from the earthquake to the around the shorter distance, so it's going out in all directions. So the odd numbers are going the far distance, the even numbers are going the short distance to our recording stations. So R2 is going the opposite direction of R1, but R3 is the wave that went the far distance around and it's now come back around the Earth again. So R3 has circled the Earth completely. R4 is circling the Earth in the opposite direction. So 6 hours out, we are still seeing Rayleigh waves that have circled the Earth multiple times. And we still have quite a bit of energy. So we would actually be able to see R5 and R6 even further out. So basically you can have this energy circling the planet for hours. And it can circle the planet multiple times for a large earthquake. Are people going to feel this? No. Can we record it? Yes. Does it give us information about the planet? Also yes. By the way, these are called record sections if you care. There are other types of seismic movement. So we can have movement that's seismic without actually generating a traditional earthquake where we have those massive fast-moving seismic waves. So tectonic creep is where we have slow incremental movement along a fault without a true breaking. It causes damage, but it's long-term damage. It's not an immediate short period of damage. We can also have what are called slow earthquakes. These are earthquakes that don't snap in a short period of time. They take a longer time to have movement. So they generate seismic waves, but they don't generate the same types of seismic waves, and they don't generate massive amounts of damage in a short period of time. It's more long-term damage. So again, this is things like you see this separation here. You see this offset that's happening here. This is happening over long periods of time. It's not a fast event. So this is not recognized by people as often as being a problem because it's happening over years. It's not happening over the course of a few minutes. How do we record these? We want to measure how the ground moves. So how do we do that? We are going to use instruments. So seismometers is the term I prefer. A lot of people will use the term seismographs. Geophones are a specific type of instrument that is a little bit cheaper but does the same thing. So the first seismic instrument was from 132 Common Era, what used to be AD. These were in China, and that's what this thing is. So this is a vessel that has a weight in the center that is attached to all these dragons that are around the outside. Each dragon holds a marble in its mouth. When the ground shakes, that interior weight will move towards one of those dragons, which will cause the dragon to open its mouth and drop its marble into the waiting frog. Not sure why they picked frogs. This tells us two things. One, it tells us that there was an earthquake, and two, it tells us which direction it came from, which is pretty impressive considering we're talking about the second century. So that's pretty impressive. We've come a long way from there. So now we actually can measure how the ground moves. We can record how the ground moves, not just that it moved. So we have what we call single component, meaning we just look at one direction of movement. Those tend to be the vertical direction of movement, so how the ground has moved up and down. The more common ones are three component. That means that we are going to look at how the ground moves up and down as well as how it moves in side to side in two perpendicular directions, and that gives us the 3D image of the ground moving. We can use springs or pendulums to do this. So we can either have a mass sitting on a pendulum, and the basically the base of that, the thing that the pendulum's hanging from, is going to be stable and the ground will move underneath it, and so the pendulum holds constant and the ground is moving, so we're recording how the ground moves by that pendulum holding constant. The other way to do it is to use a spring. This is what we commonly use now, and that spring is going to be moving, and so at this point the pendulum is what's moving, not the ground. Well, the ground is moving, but it's basically holding that that spring constant, so that the mass is recording how the ground moves. The old-fashioned ones had an actual pencil or a pen that is writing on the paper. We don't do that anymore. Now we do things with magnets and masses that move through the magnets, and they have electronic signals. We do These ones with these electronic signals are better because we can control more of the signal, and so we can make sure that between different instruments we get the same signal. So earthquakes are very dependent on what the instrument is. So like if we look at these old-fashioned ones that have a spring, depending on your spring, if you have a looser spring or a tighter spring, you may get a different response. So we will adjust our instruments so we get the same response out of each instrument. That process is called damping. So we want to make sure that even if we're using different instruments, they will give us the same response, or if we're having those instruments in different locations, then we get the same response so we can directly compare them. What they actually look like now are these. So this is maybe what you think of when you think of a seismometer. That's not what we use anymore. We used to use those, but we don't use these anymore. It's messy. It's not very accurate. It's also not digital, so it's harder to work with. And one of the things you can think about, we can see it here. This is an earthquake. These are also earthquakes, and they're overwriting each other. So if you have a really big earthquake, it will write into the past because this is earlier in the day, and this is the future. So it will write into the past and the future. So that makes it difficult if you have a bunch of earthquakes all occurring after each other, like say aftershocks. Now it's all digital. This is what the inside of our seismometers look like. So it's all digital, it's all masses. They're also much smaller and easier to transport. So this one's about the size of a bowling ball. It costs maybe 20, 25 grand. This one's about the size of a coffee can. Those are the ones I used to use. There's still some of the ones that we had at my last institution. They're out in Africa. They're about the size of a coffee can. They're maybe like 8 or 9 grand a piece. These are those geophones, which are they are put out in what we call active source, meaning that we're not going to leave them out all the time. We are going to put them out, and we are going to make the ground move and record how the ground moves to understand the ground in a local area. So this one with 3 feet is going to tell us all 3 directions. These ones with single feet tend to be just up and down. If you ever go to the Museum of Natural History at the Smithsonian, their earthquake exhibit has one of these guys. It looks almost exactly like that. These are the ones that my university in Philadelphia owned. So here I'm testing them. So this thing back here is the actual seismometer. These things are the brain of the seismometer. So the seismometer will talk to this white box through this very expensive cable. The cable itself costs like over $1,000. And this is where the data is being recorded. There's also a little GPS so that we know what time things happen. We have to have a very accurate clock. This is the seismometers again. So we have to have a very accurate clock because we need to know exactly when those seismic waves hit or arrive at a certain area. So this entire thing, each one of these, this is about $8,000. The cable's about $1,000 or so. The white boxes are also about $7,500. So I guess all told, it's too early. My brain won't do math. All told, these things are maybe about $16,000 a piece for just the instrumentations that these 3 pieces of instruments, and then there's other stuff that goes on it. Still cheaper than this one, where this thing by itself is $20,000 to $25,000. These are also much easier to carry with you. They're much smaller. I can fit a couple of these in a backpack. These particular ones are very heavy, so you don't want to put a couple of them in a backpack, but they're much easier to transport. So one of the things we always want to know is the size of an earthquake. This is what people care about, right? So size is magnitude. Magnitude are on different scales. If we're doing a regional earthquake, we use what is called local magnitude scale. It is not Richter. If you hear anyone telling you a Richter magnitude for an earthquake, they are wrong. Richter is no longer used. It used to be used, but it's no longer used. We also have a magnitude scale that's based off of the body waves. So that is the intensity of those waves that move through the earth. We have magnitude scales that are based off of the surface waves. And then the one that we use for large earthquakes is called moment magnitude, which is based off of the amount of energy released. So the local, body, and surface wave magnitude scales all look at the amplitude of arrivals, which means how high do these wiggles get when we record them. They will depend on the materials that the energy is moving through, the distance the earthquake was, etc. Moment magnitude is looking at the size of the fault, the materials of the fault, and the amount of movement of the fault in order to calculate the energy released. And so it's the only one that's accurate for these really big earthquakes. So all the scales will be normalized to be similar so that the numbers make sense, which is actually based off of Richter. But we don't use Richter anymore. So Earth has a very interesting pattern where we see that the bigger a thing is, the less frequently it happens, which is a good thing. This is true for earthquakes. It's true for large impacts. It's true for large volcanic eruptions, large storms, everything. The bigger things happen less frequently. The smaller things happen more frequently. And we see this pattern in earthquakes. So here we have magnitudes, and we have a descriptor, and then the number of events we have in an average year. So 8 and higher are called great earthquakes. We only have about one of those a year. The 9, the massive earthquakes, we have maybe one of those a decade or every couple decades, which again is a good thing. Major earthquakes would be 7s. Again, we have 10 to 15 of those. Notice these are going up by a factor of 10, so 10 times each step. That's what we mean by a logarithmic scale. So right now an earthquake is occurring. It is probably less than a size 2, but it is occurring. So it's probably occurring on a mid-ocean ridge or maybe in a subduction zone. But each of these steps we have 10 times more as we go down. The largest recorded earthquakes, again, are all above a magnitude 9. If we look at these, this is the course of 70 years or so, and we've had 5 of them. So they happen about one every decade now. Again, these are recorded. Not all recordings are going to be the same, so these values will change with time. It's really hard to get a good magnitude for these large earthquakes, especially these 3 that are all happening before we had decent recordings. These 3 are recorded on those drums where they're writing over past and present data. And actually there's a limit on how far that pen can draw. So for these very big earthquakes, we're not going to get the best, we're still estimating these. Magnitude scales are how we estimate the size. There are calculations for them. I do not expect you to know these calculations. I'm just showing them to you. They all have these constants that is designed to make them all look like the same types of numbers. So local magnitude is for small earthquakes, typically small earthquakes, that are fairly close. This is the old Richter. It's not Richter anymore. Richter is a specific location and a specific instrument. Now we call it local magnitude. Surface waves use more distant, or for more distant earthquakes. They work for deep earthquakes. You can't use, they do not work for deep earthquakes. They have to be shallow earthquakes because they're using surface waves. We have to also correct for the local geology because it depends on what rocks we're moving through. Body waves work for deep earthquakes that don't have those surface waves. Again, we have to correct for that depth as well as how far it's moved. And then moment magnitude is the one we like to use. This is the only truly accurate one for large earthquakes. And it's looking at things that are not used in these other calculations. It's also looking at the energy released. Again, you don't need to know these equations. I'm just showing you. So moment, seismic moment, measures the energy released. Moment magnitude gives a measure of the size. And again, we have these different magnitude scales that all have an M in them, but they have a different subscript telling you what they're using to calculate the magnitude. They are all logarithmic, meaning that a magnitude 2 is 10 times the size of a magnitude 1. And that's the size of the earthquake. The amount of energy, however, goes up about 32 times with each step in the scale. So the energy goes up much quicker than the ground motion, than the size. Your lab may show you something like this. This is another way of estimating these different sizes. So we can look at the amplitude of the waveforms, the wiggles, and then we can, this scale bar thing looks at the time between the P and the S arrival, which is going to give you the distance basically. If we look at that on our waveform and then we look at the amplitude and we connect them, this would then give us our magnitude. This is the least accurate way of doing it, but it just gives you a demonstration of how the you have to correct for how far away you are. The closer you are, the more amplitude you're going to have, just because you're closer, so you have to correct for that distance. So I want to now show you a demonstration about this logarithmic thing. So this is looking at energy released by the earthquakes. So we're going to go from a small earthquake to a big earthquake by looking at how many pieces of pasta that we're breaking and how easy it is to break. So this is using 30 times. It's actually 32 times. So that's a magnitude 5 would be 1 noodle. A magnitude 6 would be 30 noodles because it's 30 times. A magnitude 7 would be 900 noodles. A magnitude 8 would be 27,000 noodles. So a magnitude 8 is more than 27,000 times more energy than a magnitude 5. Let me show you that again. So the energy released in these earthquakes, when we go up by step, it's going up by 32 times. It goes up very, very, very fast. These big earthquakes are much, much bigger than the mid-sized earthquakes. Negative values are actually possible and recorded for earthquake scales because they're that logarithmic scale. We also have a problem called magnitude saturation. So each of the scales works best at certain sizes. And then all of the scales have those constants that convert them to a standardized number. So this example is showing us that we can calculate a size on each scale for certain earthquakes, but we see different values for all of those earthquakes. So if we look at, these are our two largest recorded earthquakes. They are 6.2 on the body wave magnitude scale. They are in the 8s on a surface wave magnitude scale, but note Alaska is bigger than Chile. So at least, they're getting better. In reality, these are 9s on the magnitude scale. The magnitude scale is the only one that accurately records these large earthquakes. If we look at this body wave scale, the 6.2 is the point where it gets saturated. It can't actually record higher than a 6.2. Any big earthquake is going to record as a 6.2. The surface wave scale goes up a little bit higher. It can at least get into the 8s, but still it's going to max out in those 8s. And that's what I'm showing here, that the surface wave scale kind of maxes out here in the low 8s. The body wave scale maxes out here in the low 6s. So you're not getting an accurate representation of the size of these very, very large earthquakes. The large earthquakes occur because they are actually breaking more Earth's surface, and that's what magnitude is based off of. Moment. Moment is based off of how big is the area that's fracturing and how much is it moving. So if we look at these 4 earthquakes, I've got them outlined down here. So San Fernando, San Francisco, Alaska 1964, and Chile 1960. San Fernando, which is a 6.6 on the surface wave magnitude, was this tiny little earthquake, and didn't slip very much. And it's a 6.6 on the surface wave magnitude. Note, if we look on body wave magnitude, it's a 6.2, which is the same as all of the other 3. The San Francisco one slipped a larger area. It slipped more. It was 4 meters. It's now a 7.8 on the surface wave magnitude. Again, it showed up as a 6.6. 7.8 is actually what it was on a moment magnitude as well. If we look at these 2 largest recorded earthquakes, this box represents how big Alaska was. It was more than 100 kilometers wide. It slipped 7 meters. Remember, a meter's about 3 feet, so that's 21 feet. That's a lot of slip. So the surface wave magnitude is 8.4. In reality, it's in the 9s. Chile, 1960, it's a much bigger area. It's a little bit different of a shape, but it's a much bigger area. It slipped 21 meters, so over 60 feet. That's a lot of slip. And it is a 9 point, mid-9s on the moment magnitude. So the scale you use matters. The bigger the amount of slip, the bigger and the bigger the slip area, the bigger your earthquake's going to be. These two are both convergent boundaries. They're the subduction zones. So we have this downgoing plate. This gives us a lot more area to slip. These are why we get those big earthquakes in subduction zones. Whereas if we're looking at our, how do I want to draw this? If we're looking at our strike slip, for example, which is what a lot of those California earthquakes are, we are looking at that plate is going that way, and then this one is coming towards us. So basically that's what that means, going in and going out. The amount of slip, the depth can only be the thickness of the crust, and then it's the length that matters. So they're always going to be smaller. They have one dimension that is fixed, whereas these subduction zone earthquakes have a dimension that they don't have a fixed dimension. They can go very, very deep. They can go very, very wide. So there's going to be a much bigger slip area. Just bigger so you can actually see it. So again, the energy release, the magnitude scales are going to be logarithmic. There are massive amounts of energy being released. So M2, a magnitude 2 is 10 times the size of a magnitude 1, but it's 32 times the amount of energy. So for each change in magnitude, you have 10 times the ground motion change, but 32 times the amount of energy. If you go up just 0.1, so going from a 9 to a 9.1, the ground motion is moving 1.3 times. The energy is 1.4 times. So this goes up very, very, very fast. So the reason we have to use a logarithmic scale is because we like to compare these smaller earthquakes with these bigger earthquakes. But a big earthquake is so much bigger than the next size down that it goes up very, very fast. So if we look at Chile and Alaska on a logarithmic scale, we can see them separated out, the difference. If we look at them on a linear scale, that's Chile, that's Alaska. And then most of these down here are all along, they're so much lower that we don't see a difference. So this is why we use this logarithmic scale. I'm going to talk about the other one in a second. So this is that logarithmic demonstration on bigger. So again, we do this logarithmic where we have one of our bases is going to be base 10. So we're going up by factors of 10 with each step up, because that way we can actually see the difference in these things that, if we're looking at the amount of energy just straight and linear, so that's a 1-to-1 ratio, they all will just like sit down here at the bottom and we don't see a variation because we have that one thing that's so big that is, forcing us to pull the scale. I love this figure. It's an older figure, but I love it. This is comparing the size of earthquakes, the numbers of earthquakes, and then other things. So we have our magnitude on this side. There is no such thing as a magnitude 10. We can't actually have it. We have the energy release on this side compared to explosives. In the middle, we have the number of earthquakes we have for that size in a given year. And then these are notable earthquakes, and these are some of the other things. So Chile and Alaska are the only thing that beats these big earthquakes, honestly, is a massive, large impactor. That's the only thing that's going to be bigger than these big earthquakes on the Earth. The largest volcano, or a supervolcano. Okay, so Yellowstone goes off, that is going to be up there equivalent. But Krakatoa is the largest volcanic eruption that we've had in recent times. It's still smaller. The world's largest nuclear test, still smaller. Mount St. Helens, which was a decent sized eruption, it falls in with these major earthquakes. The Hiroshima atomic bomb is only a moderate earthquake. Other bombings are way down here. Okay, the Oklahoma City bombing is way before any of your time. It's like way down here. So earthquakes have this massive energy release. They are just one of the most destructive things on our planet. The number of earthquakes per year, again, is going to be related to the size. So we have more of these small earthquakes, and they will go up by a factor of 10 each time. So we go from 20 to 200 to 2,000 to 12, So we're going up by a factor of 10 each time. That's what we mean by logarithmic. Again, this is how much the ground motion changes. That's the magnitude. The energy goes up much faster. I will show this again. So the energy goes up by a factor of 32. This demonstration is using 30. So the energy released goes up much, much faster, which is why those magnitude 9s just flatten the magnitude 8s. Okay, another way to look at earthquakes is their intensity. The intensity is how much shaking is felt. So the United States Geological Survey has a website called Did You Feel It? So you can actually report if you felt an earthquake, and it uses those reports to make shake maps. The modified Mercalli scale is not a magnitude scale. It is a scale that is looking at the amount of shaking, and it goes by Roman numerals from 1 to 12, 12 being the highest, and then uses things like you had your window shaking, you had things fall off the shelves, teacups will rattle. And so it's how much you feel it, which is really depends on what the ground surface is. For example, when I was in grad school, there was an earthquake that occurred locally. I was awake at the time. I was in my parents' basement exercising. My sister called me and she's like, "Did you feel the earthquake?" And my sister lived 3 miles away from my parents. I think she was living in her house at that time. If not, she was living in University City and my parents were in Webster Groves, which is maybe like 10 miles. She was fairly close. My sister felt it where she was. I couldn't feel it where I was because of the building that I was in, as well as, the local geology. So how much you feel is very much dependent on the materials. When we make these maps, we will use isoseismals, which are areas of the same shaking. And so this really depends on local geology. So this map is showing us the isoseismals from the New Madrid 1811 earthquake, which has been estimated as a 7.2. So we have the most shaking, locally, but we do have shaking all the way along the East Coast. And this is, again, has been figured out based on reports from newspapers and such from the time. Here's an example from California. So again, you're always going to have the most shaking close to where the earthquake occurred, and then you have less shaking as you move out. Here's an example from Northridge, and then an example from the Cascadia region. And this just shows you how much the local geology impacts it. So this 1994 Northridge was a magnitude 6.7. We see much greater shaking in the center area, and it goes out further. So I want to point out my scale here. This scale is 10 miles, this scale is 20 miles. So this image is 2 times the distance as the California image. This one in Washington State is from 2001. It is a magnitude 6.8. We don't see as intensive shaking at all, and it doesn't go very far. It goes out further, but it's less intense. Yes, that's what I want to say. Whereas the California one, it's very intense and stays very close, but it stops. It doesn't go terribly far. So this is based purely on the geology. How much it moves is going to be dependent on what rocks it's moving through. Certain rocks are easier to move through than others. So the amount of shaking is going to be determined by the magnitude of our earthquakes, obviously. The distance to the epicenter, the closer you are, the more shaking you have. The depth of the focus or hypocenter, deeper earthquakes have less shaking because the energy has to move further. You have to think about, are your distance, is your epicenter really far from your hypocenter as well? There is an idea called super shear. So this is the idea that depending on what direction you are from the earthquake, you can actually have the seismic waves moving faster or slower based on how they're moving along the fault. And so if they're moving faster, you will get more shaking. And then finally, the local geology is a big impact. So you can have amplification. Certain things shake more than others. You can also have what's called focusing. So when Mexico City gets hit by an earthquake, because it's in an old lake bed, that lake bed basically will bounce the seismic waves back and forth within it. And so you get amplification of the shaking, and it focuses there, and it's much, much worse. We have less shaking in hard rocks, more shaking in soft rocks. If you have unconsolidated sediment, that's where you're going to have your worst shaking. So the 1906 earthquake in San Francisco, we had a lot of shaking in those softer things. The earthquakes that have occurred in that same location afterwards, the fill that was put in after that 1906 earthquake, it shakes very badly, so it makes the shaking worse. So here's some examples of damage. This is what I'm looking at here. So where we have this fill and mud, you're going to have the worst shaking, this darker orange. The gray is going to have the least amount of shaking. So we had a concentration of the shaking in the areas where we had, this is the 1989 Loma Prieta. So we had the worst shaking in the areas where we had fill in from previous earthquakes. And part of the reason this one had such a high death toll, I'm sorry, this was not one. I earlier said that Loma Prieta was unexpected. That's not why it had a high death total. Freeway collapses are why it had a high death toll. We had this happening. That's two pieces of freeway that no longer have space between them. If you sandwich a freeway, you're going to have major problems. So basically, depending on what your ground surface is, depending on what your local geology is, you will have either worse shaking or not as much shaking. Another way of looking at this, so looking at an earthquake from central Virginia, it is felt across the entire eastern side of the country because of what the geology is, whereas an earthquake felt in California, it is only felt in California. So older continental crust transmits the shaking much further than younger material. How do we locate an earthquake? All right, so locating earthquakes is one of the goals. We want to know how to locate an earthquake. You will have to do this in lab. The way we locate an earthquake is we look at what are called the first arrivals. So first arrivals are the first amounts of energy that come in, which will be P waves. We look at when those things first come in. We also want to look at when the first S waves come in. So the first P waves will come in first, obviously. Then their S waves will come in. We will look at the distance between that P wave and that S wave. The S wave travels at a proportion of the velocity of the P wave, which means as you are further and further away from the epicenter or from the hypocenter of your earthquake, the S wave and the P wave will get further apart at that distance. So we can determine how far apart the first P wave and the first S wave are, and that will tell us how far that energy has traveled from the earthquake. So that tells us our distance from the earthquake. If we know the distance from the earthquake, we can then draw a circle around the location where we recorded that energy, because we know the distance from that location to where the earthquake had to happen. If we have three of those three circles should intersect somewhere. They won't always perfectly intersect because most times the earthquake's not at the surface, it's a little bit down, but they will get close. If you only have two data points, if you draw two circles, they theoretically can intersect at two places, so you need that third one to determine which one it is. In reality, we are doing a similar thing, but with much better mathematical calculations. So, this is the idea of how we locate earthquakes. In reality, we're doing this with many more stations, seismic instruments, and then we will use math to do it. We're not drawing circles. So the terms we use in location are going to be first arrival. That's the first time the wiggle comes in. So the energy, we get a first arrival of the P wave and we get a first arrival of the S wave. Origin is the time and location of the event. Hypocenter is the actual location of the origin, so it's the location part of the origin. Focus will be the same as hypocenter. And then epicenter is where you project the hypocenter onto the surface. And that's, again, what we think about, or that's typically what's reported on the news. And then the station or receiver is where we're recording that seismic energy. That's where we are recording the waves. It will not be where the earthquake occurs. You don't have to know this. How do we visualize earthquakes? So we do this with beach balls. Beach balls are a visual way of plotting what type of earthquake we have and where we see the different energy. They give us a lot of information, actually. So if we see a beach ball that looks like this, it is immediately going to tell us we have a strike slip fault. So we are seeing motion that goes in this direction. If we see one that looks like this with light in the center, that tells us it's a normal fault. So we are seeing motion in that direction. And if we see one with a dark in the center, that tells us it is a strike slip, or I'm sorry, it's a thrust fault. And so we are seeing motion in, how do I want to do this? Oh, I drew that on the wrong side. So I'm going to do it this way because I drew the other one on the wrong side. So basically a seismologist would be able to determine what type, this is a very quick way of plotting this so that I don't have to have all of the different station information. The way we figure this out is by looking at, does this thing come up or down first? So does it drop down first or does it push up first? These ones in the light color, they will pull down before they go up. These ones in the dark color will push up before they go down. And we can plot the different station locations and what type of, is it a push or a pull? And then we can figure out which ones all group together. And that's how we make our beach ball. Again, you don't need to know this. In the US, what areas are at risk? I already showed this. This is the hazard map. So Alaska, Hawaii, all along California, and then we do have these other historic areas of seismicity that at some point will have earthquakes again. All of the United States, all of North America, or northern North America. Notice the middle of Canada doesn't have a lot of earthquakes. That's because this is nice, stable craton. This is old continental crust that doesn't actually have a lot of tectonic activity. However, all along the sides of it, we have more of that tectonic activity. So where do our earthquakes occur? Plate boundaries. All 3 plate boundaries have earthquakes. We can also have earthquakes wherever we have volcanoes. So remember these maps that I showed you during the plate tectonics week. Your plate tectonics lab asks you, if you plot the earthquakes, what are you outlining? You're outlining the plate boundaries. So we have 3 types of stress, 3 types of faults, 3 types of plate boundaries. So tensional stress makes normal faults. This happens at divergent boundaries. Compressional stress makes reverse faults. This happens at convergent boundaries. Shearing stress makes strike slip faults. This happens at transform boundaries. If you ever hear the term thrust fault, that is a reverse fault that is just a shallow reverse fault. A lot of people use them interchangeably. Reverse is a better term. So where else can we have earthquakes? We can have them at intraplates. So that means it's not a plate boundary. So New Madrid and Charleston are both in the middle of the North American plate, so it's not a plate boundary. So that is called an intraplate earthquake. They are dangerous because we are not anticipating them. So this New Madrid one is still considered the largest intraplate. Also, hotspot volcanoes would be where we have intraplate earthquakes. The New Madrid ones are because the reason that they occur here because they're North America tried to break apart. The Mississippi River flows down what's called a failed rift. That is still an area of weakness in the crust, and so we have stress there still, and that's why we get earthquakes in that area. There are hazards beyond the earthquake itself. So we can have tsunamis. I will talk about tsunamis. We can have fire. So San Francisco, 1906, most of the damage in that earthquake was actually due to the fires afterwards. We can have landslides. We're shaking the earth. So that's what we're seeing up here. We're shaking the earth so we can have movements of the earth. The ground is moving. So this is the Denali pipeline. And it is on these rolling tracks because they know that it goes across a massive fault. And so they put it on this rolling track so that if that fault moves, that you're not going to break the pipeline, that it can, has a bit of give. Liquefaction is where that ground surface turns into basically fluid. Basically, when you shake certain sediments, they will just become fluid. When you stop shaking, then they freeze again. They solidify. These buildings have literally sunk into the ground because the ground has started shaking, and then they get stuck there. We have changes in elevation, so we are dropping up or raising down ground surface. And then anytime you have disruption in things, you get diseases. So disruption in water, sewage, etc. What good can come from earthquakes? I stole these slides from my natural hazards class, which I always like to talk about. What is the good that comes out of earthquakes? Earthquakes actually have a lot of benefits, which seems weird to say. So we have faults will form traps where we can have materials that we like to use and mine collecting. So groundwater and carbon fuels like oil. We have minerals that form along faults, so a lot of them are mineable. We create new landform. One of the important things is we are reducing stress. So when you have a fault break, that means you're not building up the stress. So if you have a lot of small earthquakes, that prevents you from having that one big earthquake. So it's better to have a lot of small earthquakes than a few big earthquakes. Fault gouge, the stuff that's made in the fault from the rock grinding, is useful in industry. Science. This is how we learn about the Earth. So this image is showing us information about the Earth's substructures that we only know because of studying how seismic waves move through the Earth. And I'm now going to show you a video that is looking at that 1964 Alaska earthquake that shows us how it fit into the story of plate tectonics. It's a very fascinating story.
Everything was in chaos.
I'd never seen anything that destructive that close up.
In 1964, Alaska was shaken by the largest U.S. earthquake ever recorded. Magnitude 9.2. Shaking went on for over 4 minutes. 143 people died. Total property loss in 2013 dollars is estimated at $2.3 billion. There were gaping fractures, massive landslides, and the destruction of water mains, gas, sewer, telephone, and electrical systems. The epicenter was in Prince William Sound, 74 miles southeast of Anchorage, yet effects were observed as far away as Texas and Louisiana. What the 1964 Great Alaska Earthquake taught scientists was as profound and far-reaching. Initially, no one understood how or why the earthquake occurred. Immediately, 3 U.S. Geological Survey scientists were sent to figure it out.
The main airport, the Anchorage International, was closed down because the control tower had collapsed and killed the operator.
And then we went out separately, mostly separately, to look at different things so we could cover 3 times as much ground.
The scientists studied the effects from the air, on land, and along shorelines. They were astonished to find that the surface was disrupted over an area larger than California, 185,000 square miles. Some areas dropped down as much as 8 feet, and others rose up by as much as 38 feet. Barnacles, once 2 feet below the ocean surface, were suddenly several feet above. Mapping this uplift and downdrop became crucial for understanding what happened. But with no faults visible at the surface to explain it, even with months of careful observation and fieldwork, the cause of the quake remained a mystery.
It was right at this time that this idea of plate tectonics, that the surface of the Earth is broken up into roughly a dozen different plates and that they move around with respect to each other. It occurred right at the time where this idea was being put forth.
One of the scientists, geologist George Plafker, considered the quake in terms of this newly forming theory of plate tectonics. He knew the theory had new crust forming at mid-ocean ridges, but there was no explanation for where this crust went.
And so the most likely one that came to mind is that the oceanic crust is being pushed underneath that part of southern Alaska at a very low angle, and there was slip on the interface between the oceanic crust and the overlying continental crust.
These 2 crusts are converging at the rate of 1.5 inches each year. Periodic slip between the crusts produces great quakes, which Plafker called megathrust earthquakes. His realization changed our understanding of these great earthquakes. Megathrust quakes are the largest known on planet Earth. They occur in areas of colliding and descending crusts, known today as subduction zones. The uplift and downdrop of large areas from these quakes is a result of the crust being compressed over years of the plates converging. It releases like a spring, which is the earthquake. Seaward areas are uplifted, while landward areas drop down. George Plafker identified this pattern common to megathrust quakes in subduction zones.
The 1964 earthquake was the first megathrust subduction zone earthquake properly interpreted as such. As a result of that, essentially every other large subduction zone earthquake around the world sort of falls in the shadow of what we learned from the 1964 earthquake.
Next, the question became, how often do these quakes happen?
One of the obvious things that everybody wants to know when you have an earthquake like this is how frequently do they occur? Could you have one tomorrow, or is it thousands of years?
Plafker and his team drilled 50 feet into the earth and collected core samples to find out. They used carbon dating to identify when past megathrust earthquakes have occurred in south-central Alaska.
It's just an example of what has happened in the past, and the analog for that is what happened in the 1964 earthquake, namely an abrupt uplift of a broad area of mud flats that are intertidal, and then sudden appearance of freshwater plants growing on that surface.
In the cores, where the remains of land plants overlie ocean sediments, this marks a moment of sudden change, a past megathrust quake. Dating the plant remains provides an age for that quake. The team discovered 9 megathrust earthquakes have occurred in south-central Alaska over the past 5,500 years. The average time span between these quakes was 630 years. Another devastating effect of the 1964 Great Alaska Earthquake was a series of deadly tsunamis. The largest, triggered by the shifting of plates when the quake began, traveled across the Pacific, wreaking havoc in coastal Oregon, California, Hawaii, and beyond. Locally, a number of extremely dangerous tsunamis occurred in south-central Alaska fjords like Whittier and Valdez. Most deaths resulting from the 1964 quake came from these local tsunamis in fjords. The scientists recognized that these were produced by underwater landslides that occurred as the quake began.
In the 1964 earthquake, of the people who died, most people were killed by tsunamis. And there's kind of two ways you can make tsunamis, but the way that the tsunamis were made right here in Whittier was by underwater landslides. There's material at the edges of these fjords here, and then it's shaken in the earthquake and it slides downward into the deep part of the fjord. That generates tsunami waves, which then hit the shoreline. And the thing that's really notable about those kind of tsunamis is that they hit the shoreline very soon after the beginning of shaking. And so here in Whittier, the first tsunami wave was really well observed out in the middle of the fjord, but within 3 minutes there were 3 waves that covered a large part of Whittier. And it killed about 12 people. There was a lumber mill located about where that hotel is in the background there. There were 13 deaths in Whittier and 12 of them were over there.
Chenega, a small native village in Prince William Sound, lost 23 people, a third of its population. Today, scientists use ocean bottom sonar mapping to identify submarine landslide deposits from the past. Additional work, like coring and dating these slides, will help refine understanding of the tsunami hazard and how often these quakes occur.
And at Valdez in particular, it looks like there may be like 6 to 10 of these big underwater landslide deposits at depth. So we know that these kind of things happen over and over again. You know, here we are at the margin of a fjord, we've got these big mountains, there's glaciers and streams eroding these things, they're putting sediment at the margins of the fjord. We have the megathrust underneath us here at about 12 to 15 miles depth. In these big earthquakes, it shakes like crazy, releases these sediments into the deep parts of the fjord, and then generates tsunamis. So if you're living at the edge of a fjord or recreating and an earthquake happens, a really important thing to do is to travel to high ground right away. You don't want to wait to hear a tsunami alarm or anything like that. If you feel strong shaking that feels like a strong earthquake, you need to head uphill right away. Don't wait till the earthquake is over.
Some of the most stunning destruction from the 1964 quake came from subaerial landslides. Extreme shaking led to significant ground failure and liquefaction in Anchorage. Massive landslides struck the downtown area, Government Hill, and in the Turn Again by the Sea subdivision.
What happened is through the ground shaking in the 64 earthquake, there were these blocks that sort of slid sideways as a result of that. And then some buildings collapsed into those areas. Sometimes the edge of a building was sticking off where it had failed underneath there. There were a few people killed as a result of the damage of these buildings in the 64 earthquake.
The widespread damage and loss of life from this earthquake led to a determination to use science to save lives in the future. Legacies from the 1964 Great Alaska Earthquake include the establishment of the USGS Earthquake Hazards Program, NOAA's round-the-clock tsunami warning centers, new building codes and innovations in retrofitting older, vulnerable structures. As part of the Advanced National Seismic System, the USGS now routinely monitors all earthquakes that occur in the U.S.
South Central Alaska here is the infrastructure center of the state, and it's also by far the largest population center of the state. And the work that we do, it involves basically the fundamental characterizing of the earthquake hazard, knowing which faults are active, which faults can produce earthquakes, understanding how often those earthquakes occur. And another part is understanding the local tsunami hazard, getting an idea how often they occur, and doing tsunami modeling to understand where people would be hit by these tsunamis.
Altogether, these programs can help predict strong ground motions from future earthquakes and minimize risks. For example, scientists learned that Valdez was so unstable and at such risk for earthquakes that the entire town was moved. In recent years, megathrust quakes in subduction zones, accompanied by tsunamis, have occurred in Indonesia, Japan, and Chile. The 1964 Great Alaska Earthquake changed our understanding of earthquakes and tsunamis, and had a profound and lasting impact on how scientific knowledge can be used to help reduce risks and save lives.
So, earthquakes give us a lot of information. We learn a lot from each one. So all of these, whenever we have a massive earthquake, we get better, we learn more, we do more. So there is always a benefit in that way. The other thing that we can learn, or that earthquakes can do, is help us protect the planet. So one of my seismology professors used to like to talk about how seismology saved the world. I talked about this when we talked about plate tectonics. After World War II, nuclear tests became very, very common. And so they started off that we could identify different people testing by using spy planes and satellites, but then people started testing underground. So if you test underground, you can't see it, but it still shakes the planet. So a network of seismic instruments was put around the planet to help designate or to help identify when nuclear tests occurred. This then became the Global Seismographic Network, the GSN, which still monitors for seismic tests as well as earthquakes around the planet. We can tell the difference between a nuclear test. So this upper one is a nuclear test. It looks very different from an earthquake. Most of the energy is right here at the beginning, whereas an earthquake has this spread out energy. People have the job that their job is to find nuclear tests and then determine the size of them. We can determine sizes of nuclear tests based off of our recordings. Humans and earthquakes, can we cause them? Small ones, yes. So fracking can cause earthquakes. We see that in Oklahoma, that we now have earthquakes where we never had them before. Fluid injection. So this is an example showing fluid injections where we are looking at the number of earthquakes, and we see they drastically reduce when we have a gap in injecting fluid. And when we start putting the fluid back in, the earthquakes start happening again. Also explosions, underground explosions. We can see, small earthquakes happening where we have a lot of explosions because we are putting stress into the ground. What can we do? We can't stop them. We can't truly predict them. True prediction means saying when, where, how big, exact time. We can't do that. But we can give ideas of when they're likely to occur, and we can prepare for them. So we know what areas are dangerous. We minimize the risk of structural failure. That is one of our key tools. We want to minimize risk of utilities failure. So for example, in Japan, when they detect an earthquake, all of the bullet trains immediately stop. They automatically shut off. And the important thing is education. Tell people what to do. So prediction of earthquakes is actually a probability. We can look at where earthquakes have occurred in the past, we can study the stress, and we can estimate what areas are most likely to have an earthquake, and we have to give a range of when that's going to happen. So it's all probabilities. So we're talking about areas that are likely to have a certain amount of shaking in a certain amount of time. But we're not always going to be perfectly accurate. So Parkfield is the perfect example. There were major events that were very systematically happening. That's what we see here, that we had this very systematic repeating events. So the estimate is that the next event is going to be in 1993 because it follows this line. This image here is from my textbook published in 2003. We see a 100% probability that Parkfield will rupture in 2003 because it still hasn't ruptured 10 years after that prediction from 1993. It finally does rupture in 2004, but it's not as large as it would have thought. So even if we have this nice pattern, it doesn't always follow that pattern. So prediction is estimates. It is probabilities. What we use are, we are going to look at our faults. Where do the faults occur? If there's already a weakness in the crust, we're likely to have another earthquake there. We look at ground deformation. Is the ground moving? Is it approaching that point where we're going to hit that threshold stress? We look at recurrence intervals. So that is, we look at past earthquakes and we try to see how close they are together. Again, Parkfield, that was recurrence intervals. It doesn't actually it changed its pattern. We can also look at what's called seismic gaps. So if we look at areas where we should be seeing earthquakes and we look at where we've had past earthquakes, that's what these two maps are doing. The area that hasn't had an earthquake recently is probably going to have one soon. So these area, this 2014 area had a big earthquake, so now we're not going to have one there for a while. We're going to look at areas like this has been a while. These ones that haven't had an earthquake recently are more likely to have an earthquake in the near future. So, this part, they haven't had one for a while. They may be up. We can look at the amount of movement along exposed faults, so the strain. So again, that's looking at ground deformation. There are other indications. They're not always very accurate. So we can look at groundwater, for example, the amount of radon. Those are not typically always accurate, and they only happen in certain cases. So they're not a universal indicator. Warning systems are our best bet. So Japan has automatic shutoffs for those bullet trains. Actually, Japan is the most prepared of any country for earthquakes. We can use a thing called citizen seismology. So I was talking about the cost of those instruments. Well, guess what? Your cell phone, if you have a smartphone that allows it to flip between portrait and landscape, that has a piece of technology in it that can record an earthquake. You can turn a smartphone into a seismometer. So citizen seismology is this idea of many, many cheap receivers that are cell phones in concentrated areas of population. We tend not to put instruments in big cities because cities are noisy. There's a lot of vibrations. That means that these sensitive instruments don't work very well in cities. But if we have thousands to millions of people that all have a cheap instrument in their pocket, that can be used. The other thing is that communication can move faster than the seismic waves. So if you're in a highly populated area, the Twitter accounts, the Twitter reports of "I felt an earthquake" actually move faster than the seismic waves themselves in the immediate area. So you can get warnings, a very short amount of warning, but you can get a little bit of warning that you can at least get underneath a desk or something. The same thing with radio waves. Radio waves are faster than seismic waves, so you get a limited amount of time. The most important thing about preparing for earthquakes is education. Know where they're going to happen. or potentially happen, know how to build to withstand earthquakes. We learn more after each earthquake. We want to understand where to put those critical facilities so we don't have those massive fires like we had in 1906. Knowing what to do during and after an earthquake as an individual person. Where do you go to be safe? Where can you go after the earthquake? And then finally learning from past earthquakes. So Japan has learned the most. They've had a couple of very devastating earthquakes and they get better each time. They know what to do. They don't have this happen again. California is right behind them. Chile is pretty close too. If we compare Kobe 1995 versus Tohoku 2011, the earthquake in Tohoku was much, much bigger. But the earthquake itself did not cause a lot of death. It was the tsunami, which I'll talk about next. So again, we see this difference between large, deadly, and costly. No earthquake is on all three lists. So that is earthquakes. Now I think I am moving on to tsunamis. Nope, okay. That is a shorter version of the video I showed you. I just wanted to double check. So that's like a condensed version of it. I like the longer version. Now I'm going to talk about tsunamis for the rest of the time. Tsunamis are addressed in your book, but very limitedly. So tsunami is Japanese for large harbor wave. These are generated by a sudden vertical displacement of ocean water or lake water. So this means you have to lift the water or drop the water. So earthquakes in the ocean floor, where you're actually lifting or dropping the ocean floor, are the causes of the largest tsunamis. Landslides can also cause tsunamis if you add material to the floor or move material on the floor. Volcanic eruptions, if they put material into the water, can cause tsunamis. An extraterrestrial impact can also do that if you have a big thing fall into the water. The important thing is it has to happen in the water. You have to displace the water column. So here are some notable historical tsunamis. This bottom one happened when I made these, right when I was making these slides. That one was due to a volcanic eruption. So volcanic material actually dropped into the floor, the ocean, and that's what generated the tsunami. If we look at great earthquakes, we've got 4 of the 5 recent great earthquakes, and guess what? They all generated a tsunami. Some of them large tsunamis. So the biggest tsunamis are going to be generated by earthquakes. So there are 2 types of tsunamis. They talked about this in the Alaska video. You have a local tsunami. So just like with earthquake waves, tsunami waves move in all directions. So if you have a tsunami happening in a trench that's off the coast of a continent, the tsunami waves move towards that continent. That's called the local tsunami. It happens faster. It can be smaller depending on where it's located, but it happens very fast. It hits that shore very quickly. We also have a distant tsunami, so then we have the waves will move across the ocean basin. So we have a lot more time before that tsunami will hit the shore. It also has a lot more water available, so they can get very big. This is looking at the Japan 2011 Tohoku tsunami. So Japan got hit very fast. It was within like 20 minutes. We saw the tsunami waves hitting Hawaii in 8 hours or so. It hit South America the next day. Tsunamis are very fast. Think about how long it takes you to fly from California to Hawaii. The tsunami moves faster than a jetliner. It really does. They move very, very fast. So the way we generate a tsunami is that you have to move that seafloor up or down, and it will displace a water column. This makes a dome that then collapses. So normal or reverse faults will move the seafloor. You can have ocean landslides that also move the water column, volcanic eruptions, or either in the ocean that outpour material, or volcanic eruptions that dump material into the ocean. So this vertical displacement makes this dome. That dome will fall. That generates a wave. The wave in deep water, where it's not interacting with the bottom, will have a long wavelength and a low amplitude. That's the wave height. So you can't actually feel it. A boat in the open water, in the deep water, the tsunami passes, does not feel the tsunami. As the wave approaches the shore, it begins to interact with the bottom. So the velocity decreases, which means the wavelength has to decrease. So the peaks of the wave get closer together, which means the wave height has to increase. So that means the waves get taller very fast and they stack up. So this is why they're dangerous when they hit the shore. They can occur off any coast of a large body of water. This includes large lakes and inland seas. There are certain areas that are going to be more prone to large tsunamis. So tsunamis are generated by uplift and drop down the seafloor. So areas that are across or near to a subduction zone are going to be more prone to tsunamis because that's where we're going to have the biggest uplift and drop down of the seafloor. So this map is showing us the areas with the greatest hazard. They tend to be either directly off a trench or across from a trench. Let me point out Sumatra, Japan, Chile, Alaska, all high tsunami hazard zones. Oh, I also want to point out the Pacific Northwest. They haven't had one, but eventually they will at some point. And yeah, it's going to be bad. Hawaii doesn't actually have, Hawaii is in danger because it's in the middle of all these other subduction zones. So all of these big tsunamis pass Hawaii, which is also why our hazard monitoring center is in Hawaii. Sumatra tsunami 2004. More than 200,000 people died. It was a megathrust earthquake, which was the largest since the 1960s. There was a large horizontal displacement, but also massive vertical displacement. The rupture area was about the size of California. It was a huge rupture area. Why did more than 200,000 people die? So the local deaths make sense. They didn't have a lot of warning time. But if we look at this map, the numbers are the numbers of people who died. The dotted lines are the times. India had 16,000 people die. They had more than an hour's warning. Somalia had 7 hours of warning and almost 300 people died. Why? The warning system was not in place. We didn't have a warning system that told us about tsunamis, and people didn't know about tsunamis. They didn't know as much. There is a story of a little girl who was a British little girl who was vacationing in the area, and she saw the ocean recede. She saw the ocean disappear when she was on the beach. She had learned about tsunamis in school, so she ran and got her parents and said, "We have to get off this beach. We have to get out of here." And she and her parents were able to tell people, and they evacuated that beach, and so they saved a bunch of people's lives because she recognized that sign is the water has receded, something is coming, we have to get away. So that is education, knowing about this. So a tsunami is more than just a big wave. It is a wall of water. It is literally the sea is rising up and coming in. Sometimes it will disappear first. So that's the story I just told. So sometimes you're actually seeing the trough of the wave first. So the ocean goes out and then it comes back in. So the wave will come in. Eventually that wave will leave. And so it's going to cause even more destruction when it's going back out to when the water's receding. So this is a long event. The tsunami is going to win every time. We are talking about a wall of water that is crashing into the ocean floor. This is not just a big wave like what you get in a hurricane. This is the ocean is rising up. And there can be multiple waves. These are not new things. We can see dead forests that tell the tales of past tsunamis, that the water just killed everything. We can also dig pits to see recordings of past tsunamis, similar to what they did with the earthquakes. And sometimes we can actually link these to a direct earthquake. So we can look at evidence of past tsunamis in the Pacific Northwest and find the earthquake in Japanese historical records that caused that tsunami, which is pretty cool. So after the waves, we're going to have flooding, obviously. You have all this water coming in. You're also going to pull away a lot of new material. But the big problem with tsunamis, besides just the flooding, is disease. We have ripped open sewage. We have dead people and animals around. We've contaminated all of our water and food supplies. Mosquitoes breed in water, so we get diseases passed around by mosquitoes. We're going to lose power. We can have fires because we're going to disrupt our gas lines. There is massive, massive damage. Can good come from a tsunami? Unlike some of the other hazards, it's not really obvious what comes. You know, you've just destroyed the coastline. Large amount of water can bring chemicals to the land from the sea, so that can aid the ecosystem long term. You'll also get a movement of sediment, so that can help develop the landscape. These are both very long-term things. There aren't any short-term things that are beneficial. For a small tsunami, I guess we learn more so that we can be better prepared the next time. If we compare Sumatra more than 200,000 people died in 2004, to Tohoku in 2011 when only 20,000 people died. That's a benefit, and that's all about preparedness. So we learn, we prepare. We can't prevent tsunamis. There is no way. It's a wall of water. We can have a warning though. So large earthquakes will trigger a tsunami warning. Other things don't. So basically we don't automatically record when a volcano goes off or a landslide. When a big earthquake occurs, we know. So if a big earthquake occurs in an area that could cause a tsunami, we initiate a tsunami warning. Then we also do have buoys that are connected to pressure sensors. They monitor the wave height, and so they can see a tsunami in the ocean basin. So those buoys, when they're in place, work well. So that's what we're looking at our monitoring system here. If they're not there, they don't help. So 2004, we didn't have this system. Now we do. It's aging, but we have it. They're not as helpful with local tsunamis. So Japan has the best system. They have the best trained population, but they still saw 20,000 people die in 2011 because there just wasn't time. But they knew it was coming. So we can try to build to withstand tsunamis. It's hard to withstand against tsunamis. We can make seawalls to try to stop the wave. They're only effective if they're high enough. In Japan, 2011, most of them failed because they didn't anticipate that big of a tsunami. We can try to predict where we're going to have the worst run-up. So we call these run-up maps. So we try to predict where the water will come in, which then helps us determine evacuation routes and safe zones. And we can also give probability forecasts. We're going to see a couple of videos that talk about all these things. We can also be intelligent with our land use. No one's going to abandon the beaches, but we can try to put trees and vegetation as a buffer. These low elevation coasts are more susceptible because the water comes up faster. If the coastal plain shallows slowly, that will lead to smaller waves. If we have a steep coastal plain, we get higher waves. We see that in Japan, that the coast rises very quickly, and so the waves grow very fast. The important thing is education, knowing that you're not going to beat a tsunami. You can't wait it out. You have to evacuate. Get up and inland. That is the only thing that can help you. And knowing where to go and how high to get is critical. So I'm not going to talk about this actually, but basically being prepared is the only thing. So having a personal preparedness, if you live in a tsunami hazard area, communities have to be prepared, and that's a bigger deal. So now I have a bunch of videos I'm going to show. The first few are about this first one's about Sumatra and the buoy system.
December 26, 2004. What began as an undersea earthquake in the Indian Ocean ended as the most deadly tsunami in recorded history, with nearly 240,000 lives lost. This was a devastating wake-up call to coastal communities and tsunami research. Prior to this event, only 6 of NOAA's Deep Ocean Assessment and Reporting of Tsunami, or DART, buoys were in place. Scientists could only predict tsunami arrival times, not flood potential. And there was not a global tsunami warning system. Today, 10 years later, we can tell a different story. U.S. and international coastlines are far better prepared for such a catastrophe, thanks in large part to research and technology developed at the NOAA Center for Tsunami Research at Pacific Marine Environmental Laboratory. NOAA's DART array is now complete, with 39 buoys operated by the National Weather Service's National Data Buoy Center. Along with 21 international buoys, this array can measure a tsunami wave as small as 1 centimeter in the open ocean and provide these data in real time to forecast when a tsunami may hit the coast and how much flooding there will be. NOAA scientists and engineers are currently testing the 4th-generation DART buoy that will be able to measure local tsunamis as well as distant ones. Flooding forecast models incorporate local topography and historical tsunami data in order to more accurately predict exactly how a tsunami might behave when it reaches shore. NOAA has 75 site-specific models that can provide high-resolution flooding forecasts for effective response and mitigation during a tsunami event. NOAA has gathered data from every tsunami since 2004 to improve its forecast models. Today, it operates the world's only real-time tsunami flooding forecast system using DART data to accurately compute flooding forecasts. The NOAA Tsunami Warning Centers make tsunami data available on the internet and issue advisories, watches, and warnings through the Emergency Alert System and via NOAA weather radios. While it is impossible to prevent a tsunami, we are now much better prepared to detect them and predict their paths and impacts, so those in coastal communities can take the steps necessary to safely protect themselves.
So we're actually getting close to being 20 years out from Sumatra. That video is a little bit old, but still, you will see in these videos different numbers of DART buoys. So this one's about Tohoku.
On March 11th, 2011, a 9.0 magnitude earthquake off the Pacific coast of Japan generated a tsunami. This series of ocean waves sped towards the island nation, with waves reaching 24 feet high. The result was devastation and utter destruction. Towns were engulfed by water and swept away. Farmland was flooded. Tens of thousands of lives were lost. The National Police Agency reported damages to hundreds of roads, bridges, and more than 100,000 buildings. The surging water flooded rivers and destroyed harbors. In some areas along the coast, tsunami waves reached 6 miles inland. Tsunamis not only cause severe damage when they first strike land, but also as the water recedes back to sea. Tsunamis can inflict this type of damage because of some unique features. As tsunami waves travel across ocean basins, they may be as little as a few centimeters high, but they extend down to the ocean floor. This is different than traditional waves, which are only surface features. Tsunamis can also travel hundreds of miles per hour in the open ocean. As these waves approach a coast, the shallowing ocean floor slows the waves down and pushes the water mass upwards. The quicker the ocean floor transitions from deep to shallow, the greater potential for a higher wave height. So, tsunamis that experience this sudden shift into shallow water can have the height and momentum to pack a serious punch. Unfortunately, Japan found itself in this scenario. This image shows how abruptly the Japanese islands rise out of the ocean. Other coastal areas in the region have much more gradual slopes. The earthquake on March 11th was the most powerful known to hit Japan, and the tsunami it created had the necessary ingredients to make it such a deadly and destructive force.
So again, if that earthquake had occurred in any other subduction zone, I don't even want to imagine what the death toll would be. Japan is the most well-prepared nation for earthquakes and tsunamis, and it was larger than they had anticipated. This earthquake and tsunami is also called the triple disaster because you had this massive earthquake followed by a tsunami. The tsunami hit a nuclear reactor and damaged one of the nuclear reactors, which then had a meltdown. So you had 3 things happening. It was massive. This next one is also about Tohoku.
These are the sounds of a tsunami warning. They alert residents that a killer wave is about to strike. These sirens, however, are just a small part of the sophisticated warning systems that played a role in Japan and in the US during the Pacific Ocean tsunami in March 2011. Most tsunamis are generated by an undersea earthquake. Fortunately, Japan has one of the most advanced earthquake early warning systems in the world. It detects tremors, calculates the epicenter and sends out warnings from over 1,000 seismographs scattered throughout the country. The Japan Meteorological Agency issues the warnings and sends alerts to television and radio channels, the internet, and mobile phone networks. When the earthquake struck 80 miles offshore, warnings were generated in about 3 seconds. The tsunami warnings came 3 minutes later. These take longer because more complex calculations are involved and must factor in ocean data. Since the first tsunami wave struck the coastline within 20 minutes, the advanced warning provided some residents with crucial minutes to reach a safe area. While the earthquake sent powerful tsunami waves westward toward Japan, the tsunami also propagated east into the Pacific Ocean. Here, warnings are issued by the Pacific Tsunami Warning Center, operated by NOAA in Hawaii. NOAA maintains a large network of buoys with ocean floor sensors that are strategically positioned in the earthquake-prone zones of the Pacific. This system collects vital ocean data for tsunami forecasting. On March 11th, only 25 minutes after the earthquake struck, the first buoy station measured the tsunami and relayed information to Hawaii. Scientists used this data to run models and issue forecasts and warnings to nations throughout the Pacific. From there, local emergency managers decided what actions were appropriate to take for public safety. The earthquake and resulting tsunami devastated the Japanese coastline, causing damage that will take years to repair. While we can't prevent these forces of nature from happening, our early warning systems can help us prepare for the dangers headed our way.
So let me say that we focus on the Pacific coast or the Pacific Ocean for tsunami monitoring because it is surrounded by subduction zones. Those make our biggest earthquakes, which make our biggest tsunamis. The Atlantic Ocean, not as worried about them, but we can still get tsunamis in the Atlantic Ocean. All right, this final one is looking at what you can do to be prepared. It's a bit, it's this interesting style, but this is what you can do to be prepared if you're visiting an area that may experience a tsunami. Oops, that didn't play. Let me actually play it.
Let's put some basic information on the table. While more common in the Pacific, a tsunami can strike any coast, anytime. It's one of the most destructive forces in nature. A series of waves, usually caused by an undersea earthquake. These powerful, fast-rising floodwaters can smash everything in their path. Even small tsunamis can be dangerous, especially to swimmers, surfers, and boats in harbors. But there are ways you can prepare. First, understand the warnings. If an official warning is issued, do what it says. Just as important, pay attention to warnings Mother Nature provides. You may feel a strong or long earthquake. You may see the ocean suddenly rise or fall, or hear a loud roar. If you experience any of these, a tsunami could be coming. Protect yourself. Quickly move to high ground or inland away from the water. Stay out of the tsunami hazard zone until officials tell you it's safe. The first wave may not be the last or the largest. Dangerous currents are possible for several hours or days. Prepare yourself by doing a little homework. Think of the places where you spend your time and map out routes to safe places, high ground or inland, away from the water. Practice walking these routes so they become familiar. Be prepared and stay safe.
All right, so that is, nope, it's not going to go. That is it for this recorded lecture. There's not going to be a lab this week. We're doing exam 2, so make sure you prepare for that. And I will see you in class.